Good morning or day or whenever you're watching this. Today we're going to be talking about lesson 3, how do clouds and storms form? All right. So let's just jump right into it. Clouds are a large mass of small liquid water droplets or ice crystals. So it's a mass of small liquid water droplets or ice crystals. All right. And that depends that what it is, if it's droplets or ice crystals, depends on how high in the atmosphere, in the troposphere, it forms. All right. There's 3 things that cloud formation requires. Water vapor. Obviously, you have to have some kind of moisture in the air in order to get condensation to happen. All right. So that already has to happen. Something called a condensation nuclei. And that is a surface for the water to cling on. So it can be like dust particles. Today's really cloudy, and over the past couple weeks, there's been fires out in California, and so they've been burning all these trees, putting smokes and dust particles up into the air. Those actually have traveled because of the way we're going to learn about wind patterns, but usually in our latitude where we're sitting on Earth, the wind comes from the west and brushes weather along towards us. So things that are happening out in California can affect us and are affecting us right now. So today, I don't know if you can see, today is super cloudy. Did you see that just happened? It's pretty cloudy. Well, let it adjust maybe. You can't really see it. I thought you could, but it's super cloudy. Obviously, it's a little bit brighter out there than it is in here, so I'm sorry about that. But you can look it up in the history books. Today's September 24th, and 2020. And there have been fires and there's dust particles in the air. And so it's really cloudy over here right now because those dust particles blew over from California. Water can cling on it. It has something to sit on. It's the same idea with like when you're in the shower and you get out and your mirror's all foggy. You can look up at the lights when you get out of your shower and you can see there's like water particles kind of like floating around, but they need something to land on in order to make a cloud. So you need you need dirty air to make clouds or something for it to land on. Cooling air. And then the third and the last thing is you need to cool the air to the dew point temperature. Okay. Right there. And that's where the air becomes saturated and water can condense. So water vapor in the air, something for it to land on, the air to cool to its dew point. All right. So here is an image of convective cooling. And you can look and say, all right, hot air is rising. So convection, remember, is where hot air rises. So hot air rises. As it rises, we can see it says cooling, rising, condensing air particles. So as it rises, and you can see the bubble expands. The air expands. It cools. And then, so hot air rises. As it rises, the air expands, it cools, and eventually it will reach dew point temperature. This will form a cloud. All right, so it has all the things we are talking about where you have hot air rising, it expands, it cools, and at a certain point, it'll reach a level where it cools to its dew point and convection occurs. Okay? Convective cooling is caused by uneven heating of the atmosphere. So obviously, areas down at the equator are warmer than up at the top. So our Earth is unevenly heated. Sun does not hit directly all over. So it's caused by uneven heating of the atmosphere. Let's highlight that. That's important. The bubble of warm air rises higher into the atmosphere where the pressure is lower The bubble expands and cools as it rises. That whole thing's underlined, so we probably should highlight it. And then this is something that you need to be aware of, but you don't have to memorize. The adiabatic lapse rate, that vocab word, it's how quickly the rising bubble of air cools. So dry air cools at a constant rate. So as you go up 100 meters, so I was going to say like a football field, but that's not right. That's yards. But as you go up 100 meters, it's going to cool 1 degree Celsius. So it goes negative 1 degree Celsius per 100 meters. Or it's a lot easier to remember 1 kilometer. As you go up 1 kilometer, it's going to cool by 10 degrees. And that's dry air. That's air that hasn't become a cloud yet. Now, once we reach dew point and it becomes a cloud, it's going to cool at negative 2 degrees Celsius. Now, we can use those two numbers to figure out how high in the sky is there going to be a cloud, all right? Or what is the level that we're going to get a cloud? That's the condensation level, the height in the atmosphere when the air bubble cools to its dew point, all right? I'm going to bold that because that's a big deal. Bold, underline, all right? This is the level in the sky where you get a cloud. So we can actually calculate, looking at an air parcel, how high it would go into the sky or have to go into the sky in order to form a cloud. So the way we do this, we take those numbers that we just found, right? Let's say we have an air parcel or a chunk of air that at its dry temperature is 20 degrees Celsius. Degrees C. All right. And the first one it has is this purple dot. This is if it was fog already, if it was the dew point. All right. So the dew point temperature is 15 at the ground level degrees Celsius. And all you have to do is say, all right, for every 100 meters, it's going to go up 0.2 or get cooler by 0.2. So I could easily go and say, all right, 100 meters, 0.2, that's tricky to draw. But if I go up to about 500, I will get it that it got cooler by 1 degree. So I'll go up, I'll put a point there, and then I draw the line across. And where those two cross, that's the cloud base height, where your temperature and your dew point meet. Remember, that's all we're saying about dew point temperature. It's the temperature you would need to cool a chunk of air in order to get a cloud. So this cloud, this cloud would form at 600 or a little bit above, like we'll say 610 feet. 610 feet. If a cloud at ground level is 20 degrees Celsius and has a dew point of 15 degrees, that means if I can figure out that the height of that cloud, I'd have to push it up 610 feet for it to get to the degrees for dew point and regular temperature to meet. Okay? Now, let's say it's drier. So we have the same air parcel. It's 20 degrees Celsius. But the dew point temperature is 10 degrees Celsius. We know already, remember, the further apart the dry bulb temperature or the regular temperature and the dew point temperature, the further apart they are, the drier the air. So we're going to have to shove that chunk of air higher up into the sky for those two temperatures to meet and make a cloud, right? We want dew point and the regular temperature to be the same. We got to shove this one higher because it's further, the degrees are further between them. All right, so and this is only 5 degrees. The dew point is only 5 degrees cooler. So you'd think like, that's not that big of a deal. Well, we push them up and you'll see where they cross. Remember where dew point and temperature meet, where they're the same, that's where you're going to get a cloud. So that's the base height of the cloud is going to be, it looks like 1,275. We'll estimate 1,275 meters. I didn't check my units when I wrote this. Meters. All right. What happens to cloud formation when the dry temperature and dew point are far apart? Well, far apart means you have to shove that air up higher in order for those two temperatures to meet. So the air is drier if temperature and dew point are further apart. So in order for the two temperatures to meet, you will have to shove the air up higher for the chunk of air to reach dew point temperature. All right, what does this tell you about the humidity of the parcel? We already answered that. It's super dry. The air is dry. So on days where you see clouds super high in the air, it's usually going to be drier. If you have like fog, the air is going to be more humid because you don't have to shove the air as high to make a cloud. Remember, fog is just a cloud at ground level. Okay, so those are some things to keep in mind there. All right, so this is how we can graph and figure out, I have this chunk of air that has a dew point of this, how high do I have to put it? You use this graph, okay, and where they overlap. And remember, this graph, this line is drawn by using this information, okay? So we know what we're starting at. For every 100 meters, we subtract 1, right? That's why this line is going, all right, if I go up 100, I'm at 19 degrees. I go up another 100 to 200, I'm down to 18 degrees. That's how we draw that line. Dew point, you go up 500 and you subtract 1. And where they cross, that's where your base cloud height will be. And that's something I really want to point out is the condensation level. We're going to use the terminology base, let me put this in bold, Control B, base height, base cloud height. Let's just double check. That is base cloud height. Yeah, I guess so. All right, base cloud height. You're going to see this terminology more often. Okay, so make sure you add that into your notes. All right, I know this was longer and it had a little more technical stuff in it, but hopefully you get the main purpose, or the main thing you'll see is the further apart the temperature and the dew point temperature, the drier it is and the higher you have to push it up into the air to make a cloud. Okay? Have an awesome rest of your day. Let me know if you have questions. Bye.